Let's talk about the equilibrium constant. So let's say if we have a reaction where A moles of this compound A, this capital A, it turns into B moles of this compound B, and at the same rate, this is turning back into the reactants. Now the equilibrium constant for this is going to be, so this equilibrium constant is symbolized by this Kc. So the equilibrium constant for this reaction is basically just the concentration of products over the concentration of reactants. So in this case, it's going to be the concentration of B raised to the amount of moles there are, right? This little b right over here represents the coefficient of the big B, and that represents basically how many moles of this big B do I have, right? And it's going to be divided by the concentration of A, the reactant, raised to the amount of moles of the reactant. So if we were to write out the equilibrium constant expression or equation for, let's say, this reaction, 2NO2 is at equilibrium with N2O4, the equilibrium constant is going to be equal to, it's going to be the concentration of our product. So the concentration of our product raised to the amount of moles of product. So in this case, we have 1 mole of N2O4, so it's going to be raised to the first power. It's going to be divided by the concentration of our reactant. So our reactant right over here is NO2, and it's raised to the second power because there's 2 moles of it. So yeah, that's basically the equilibrium constant, right? It's just going to be the amount of products, the concentration of your products, divided by the concentration of your reactants, okay? So products. If I were to add, let's say, if I were to kind of extend this reaction like this, or let's say C moles of this compound plus A moles of this compound, and it's in that equilibrium with B moles of this and D moles of that, right? The equilibrium constant would be this right over here. So you have the concentration of your products. So in this case, my products is B and D, and they're raised their respective moles. And it's going to be divided by the concentration of our reactants raised to their respective moles. Notice how I'm multiplying these two values together, but ultimately, remember, the trend is that it's still going to be products divided by our reactants, right? So let's do a little example. So let's say if I have this reaction, this N2, it's at equilibrium with 2NH3. Let's say this is at 400 degrees Kelvin. All right, your equilibrium constant is always going to be for a specific temperature, 0.1 molar. And let's say if this 2NH3, there's a concentration of, let's say, 0.15 molar. And this is all made up, by the way. So if we wanted to calculate the equilibrium constant for this, it's just going to be the concentration of our reactants, NH3, raised to the amount of moles of NH3. So it's going to be to the second power. And this is going to be divided by the concentration of H2 raised to the third power, right? Because 3 represents the amount of moles of H3. And then this is going to be multiplied by the concentration of N2 raised to the respective moles. So there's 1 mole of N2, so it's raised to the first power. All right. So remember, once again, this is trend of concentration of products over the reactants, the concentration of reactants. Now we could just plug our values in. So plug in 0.15 here, 0.1 here, 0.2 here, and then you should get the answer. But, you kind of get the point, right? You get the point of how to, Let's say if I wanted to write out the equilibrium constant equation for this reaction. Now, you would actually do kind of the same things you did before, right? Concentration of products to the amount of moles there are and divided by the concentration of products. But notice how we're not actually including the concentration of carbon at equilibrium. Why is that? It turns out for the equilibrium constant that when you're writing this out, you actually don't include the concentrations of solids or the concentration of liquids, pure liquids. You only include the concentrations for your aqueous solutions and your gases. Now, why is that? Well, the thing is that the concentration for the solid and the pure liquid actually doesn't change over time. Think about it. Let's say that if I have like some sort of solution filled with water, if I add a lot of salt to it, remember that molarity, aka the concentration, is equal to the amount of moles of your solute, aka our salt, right? It's the amount of salt ions I have in this case, right? Na ions, Na plus ions, divided by the amount of liters, right? It's moles over liters. In this case, right, if I take a scoop out of this, water, well, there's going to be a lot of moles of salt because I placed a lot of salt in here, right? So it's going to have a high concentration of Na plus ions. So if you add more Na plus ions, it's going to increase the concentration of Na plus ions. However, let's say if I'm dealing with a pure 100%, zinc metal. Let's say if I'm dealing with zinc metal. Let's say if I take a chunk out of this zinc metal, I'm going to get 100%. I'm going to get, let's just say 100% pure zinc. All right. If I take a little scoop out of this. Now, let's say if I add more zinc. Let's say if I add more zinc to this mix. Well, the thing is that if I take a scoop out of this zinc chunk, it's still going to be 100% pure zinc. So you kind of get what I'm saying? Like, when you increase the amount of solid that you have, you're only increasing the mass of the solid. You're not actually increasing the concentration of the solid, right? For a lot of people, they get confused because for a pure solid or, 100% pure liquid, adding more of that thing does not increase its concentration. It just adds mass or, it adds volume, but it actually does not increase the concentration of it. Only gases and aqueous solutions like the one here, the concentration changes when you add more of it. All right, so that's kind of the thing that's important. Now, equilibrium constant can tell you a lot about, a certain reaction. Remember that the equilibrium constant is basically just the concentration of your products divided by the concentration of your reactants. Okay? Now, if your equilibrium constant is much, much, much greater than 1, let's say if it's 3.8 times 10 to the 8th power, that means that the reaction is product favored. And the reason why is because if you want to have such a big number, you got to have a big numerator, right? So in this case, the amount of products has to be really big, right? Because it's in the numerator. So if your equilibrium constant is much, much, much less than 1, like this right over here, then you must have a very big denominator to make your value small, right? And what's in the denominator? The concentration of your reactant, all right? So the concentration of your reactant, imagine if this value was very, very, very big. Well, then you're going to have a very, very big denominator. So if you're dividing something by a very, very big denominator, you're going to get a very, very small value. So yeah, this reaction is going to be more reactant favored. Now, you also have something known as the reaction quotient, which is basically just the equilibrium constant, except you can take it in any moment in time. So for the equilibrium constant, right, the concentration of your products and the concentration of your reactants, they have to be the equilibrium concentrations, right? So if I were to zoom back into this reaction right over here, the equilibrium constant expression is equal to the concentration of H2 at equilibrium times the concentration of carbon monoxide at equilibrium divided by the concentration of H2O at equilibrium. So all of these concentrations have to be at equilibrium because this is the equilibrium constant, right? But for the reaction quotient, it doesn't have to be at equilibrium. You can take the reaction quotient at any moment in time. And you might be wondering, why is that useful? It's literally the same. Imagine the equilibrium constant, but you can take it at any moment in time. So if it's literally the same thing as the equilibrium constant, why do we use it? And the sole purpose of having this reaction quotient is so that you can compare it to the equilibrium constant. So in this case, let's say if I have an equilibrium constant of 1,000, just to simplify things. And let's say if this is at 400 degrees Kelvin, and let's say my reaction quotient for this reaction is 100, and it's still at 400 degrees Kelvin, my temperature is constant because temperature actually affects your equilibrium constant, because your equilibrium constant, remember, is the concentration of products over concentration of reactants. And the thing is that if you increase or decrease the temperature for a certain reaction, that can increase and decrease or decrease the concentration of your products. It can increase or decrease the concentration of your products and reactants, depending on whether the reaction is exothermic, or endothermic. And for this, you kind of have to know Le Chatelier's principle. So if you don't know that, I highly recommend y'all to, check that out. But, from Le Chatelier's principle, hopefully you guys will remember that if you increase or decrease the temperature, well, depending on if the reaction is exo or endothermic, it's going to shift the reaction in a certain way, altering the concentrations of your products and reactants. So that's going to be something important to know. Temperature affects equilibrium constant. Now, in this case, notice how your reaction quotient is actually less than your, or let's say this first. first of all, you kind of notice that the reaction quotient is not equal to the equilibrium constant. And that means that the reaction at this certain moment, so at the moment in time when you take the reaction quotient, your reaction is not at equilibrium, right? The equilibrium concentration, all right, it's 1,000, but your reaction quotient, you took it at some moment in time and it's not 1,000. So your reaction is not at equilibrium because the concentration of the products and the reactants, they're not the same as if it was in equilibrium, at equilibrium. Also notice how QC is actually less than KC. Now, what does this mean? This actually means that your reaction is going to shift to the right, aka you're going to start making more products. Now, let's think about this logically, right? So my equilibrium constant is 1,000 and my reaction quotient is 100. I want to get from 100 to 1,000, right? Because this right over here is not at equilibrium. I want to get to equilibrium, right? Remember Lee Chatelier's principle, right? You got some sort of disturbance, right? Your reaction is just somehow magically going to come back to equilibrium. So how do I get from 100 to 1,000? Well, I have to increase my numerator. And what's in the numerator? The products. So if I increase the amount of products I have, that increases my numerator, which then increases my value, right? For going from 100 to 1,000. So in this case, this reaction is actually going to shift to the right. I'm going to start making more products so I could get my product concentration up so that I can get to the equilibrium constant. Now, and you use basically the same logic for the fact that if your equilibrium constant, if your equilibrium constant is actually, let me do this actually. All right. So if your reaction quotient is actually greater than your equilibrium constant, the reaction actually shifts to the right. Because think about it, right? Let's say if your reaction quotient is equal to 1 and your equilibrium constant, let's say that's equal to 0.1. Now, right now I have a very big value and I want to get to a smaller value. So what do I have to do? Well, I have to decrease my concentration of products and increase my denominator, right? If I increase the denominator, my value will get smaller, right? So how do I increase the denominator? Well, my denominator is the concentration of reactants. So my reaction is going to shift to the left, aka to the reactants side, so that I can form more reactant. So my QC will eventually get to KC.